Modern flight relies on automated systems to catch human errors before they become fatal. But when those systems glitch, they can transform from invisible protectors into active threats that pilots must physically wrestle to overcome. Wide-body jets are built with deep layers of digital redundancy. Multiple onboard computers constantly cross-check each other, theoretically preventing mechanical failures before a human crew even needs to intervene. To understand the limits of that redundancy, we have to look at the case of flight AI171. This was a flagship Boeing 777-300ER, commanded by a captain and first officer with over 23,000 combined flight hours. The afternoon began with absolute normalcy. Passengers checked in under the bright lights of the Ahmedabad terminal, boarding a plane that had passed every pre-flight inspection and fuel verification. When the engine surged for takeoff at 6:38 p.m., every sensor and manual check confirmed a flawless departure. The flight data shows the exact moment that routine ended. The aircraft climbed steadily until it hit 3,000 feet, and then the altitude line suddenly spikes into a jagged, uncommanded dive. In the Ahmedabad Air Traffic Control Tower, the quiet evening was shattered by a fragmented radio call. At 6:42 p.m., the crew broadcasted an urgent mayday. The pilots used specific, chilling terminology over the radio: manual override and losing altitude. This confirmed they were actively fighting the aircraft's own control logic. The struggle was short. Radar contact was lost exactly 3 minutes later. A state-of-the-art aircraft with healthy engines had effectively rebelled against its crew, leaving investigators to determine how a functioning plane could crash itself. Recovery teams eventually located the orange flight data recorder among the debris. This device provides the only objective record of what was actually happening inside the cockpit's computer brain. Investigators extract millions of data points to reverse engineer the crash, recreating the digital environment the pilots experienced second by second. This data reveals a stark contradiction. On the left, we see the pilots pulling back on the yoke with maximum force to lift the nose. On the right, the aircraft's automated stabilizer is executing the exact opposite command, driving the nose toward the ground. To resist the automation, the pilots had to exert massive manual strength, physically fighting the weight of a 300-ton machine. The data captures a modern crisis, a scenario where programmed certainty overrides human experience. Engineers define this breakdown as a cascading sensor failure, where one piece of corrupted information triggers a lethal chain reaction through the ship's computer. The flight computer relies entirely on external sensors. If one provides false data, like falsely signaling an aerodynamic stall, it pollutes the entire system. To save the plane, the logic dictates an aggressive pitch-down command, prioritizing this defense mechanism and cutting off the pilot's manual inputs. This design created a tragic outcome. The system was engineered to ignore the pilots, its math assuming the humans were making the mistake. The investigation into the root cause of that sensor anomaly remains open. These officials are coordinating a rigorous inquiry to determine why the automated logic failed so catastrophically. While the report isn't final, the data has already ruled out engine failure and pilot error. The crew did exactly what they were trained to do. Engineers are now using advanced flight simulators to replicate the exact sensory conditions of the crash. They need to see if this software reaction can be triggered again in a controlled environment. Until that root cause is identified, this specific vulnerability remains a theoretical threat to any airline operating similar software architectures. The industry has responded with an immediate global mandate to review how pilots manually override automated systems. There is a new urgency in pilot training to recognize when a computer is operating on bad data and when it is necessary to stop trusting the machine. This tragedy is forcing a larger discussion about the assumption that digital redundancies are always safer than human judgment. As aircraft become more autonomous, safety depends on a single rule. No matter how smart the code becomes, the human crew must always retain the final authority to pull the plug.